All right, already took roll. Just as a very quick review of what we had gotten through on last Tuesday, I guess maybe. So what we had found was that the field energy, W sub F, was going to be equal to the magnetic flux density, so B field in our core, squared over twice times the permeability of our core times the volume of our core. And then we were also going to have a very similar term for our air gap. So it's going to be Bg squared over twice mu naught times Vg. And I told you guys that I wanted to kick things off with an example problem. So let's do that here. Okay. So I'm going to redraw our relay circuit, essentially. Let's put my core over here. Drawing it a little bit bigger than last time, but you guys will get the gist of it. Wire around this bad boy. Like so. So we've got some number of turns ends that I will define here in just a moment. Let's see, what else do I have? Here's my resistance R. Let's say that this is 5 ohms. Let's say that our core has a permeability of 5,000 mu naught. Our air gap length LG is 5 millimeters. And I'm going to give you some dimensions on this guy right here. So let's say that this part is 10 centimeters from here to here. This width right here, 5 centimeters. Thank you. This width right here, 5 centimeters. This distance right here is 10 centimeters. And this distance right here is 5 centimeters. And I think that's all we should need. I'm just going to make a note that this distance is my air gap. And I want us to find the DC voltage necessary to establish a 1.0 Tesla magnetic flux density in the air gap. And the energy stored in the coupling field. Okay. So let's run through this guy really quickly and figure out what the equivalent reluctance of this magnetic circuit is going to need to be, because that, as per usual, is going to be related to voltage and current in our magnetic circuit system. So in this particular case, I'm going to have effectively Req will be the reluctance of my core plus twice the reluctance of my air gap, because there are two air gaps in this simple system. So what is the length of my core? Let's start there. Okay. So I believe that I've got this full 10 centimeters down here, and then I've got half of 5 centimeters. I've got half of 5 centimeters, so that's going to look like 15 centimeters on the bottom. Exact same distance on the top, so this part contributes another 15 centimeters, and it looks like this guy is going to be 15 centimeters, 10 plus half of 5 plus half of 5, and this part right here is also going to be 15 centimeters. So overall, 15 times 4 is 60 centimeters.
Plus 2 RAG.
Yes, the reluctance of the air gap. So to me, it looks like I'm going to have 60 centimeters. So that's my length of my core over 5,000 times 4 pi times 10 to the minus 9 henries per centimeter. Where did I give you guys the thickness? Yeah, that's what. 2 times. So my air gap length is 5 millimeters. So I'm going to write that as 0.5 centimeters. My permeability is just 4 pi times 10 to the minus 9 henries per centimeter. And then my air gap area is going to be 5.5 centimeters times 5.5 centimeters. Just to remind you all, I'm coming up with that 5.5 centimeters for both of those dimensions because I usually just add the length of my air gap to each of my cross-sectional area dimensions, right? So since my thickness was 5 centimeters, I have 5 centimeters plus LG is 5.5 centimeters. Since my width is 5 centimeters plus LG is going to look like 5.5 centimeters. So jumping ahead straight to the answer here, we're going to wind up getting 2.669 times 10 to the 6th amp turns per Weber. The magnetic flux that is flowing around in our core is going to be the flux density in our core times the area of our core. So for what it's worth, that's just the 1 Tesla. So I'm going to write that as 1.0 Webers per meter squared, because that's the same thing as a Tesla. And then I have an area of 5 centimeters quantity squared. And to make the math come out better, I'm going to do 1 meter over 100 centimeters and square that guy as well. And we'll wind up having 2.5 milliwebers. From this, our current is just flux times Req over the number of turns. So that is 2.5 times 10 to the minus 3 Webers times our equivalent reluctance, 2.669 times 10 to the 6 amp turns, per Weber. divided by, let me scroll up here. I did not tell you, so let's just do it here. N is 250 turns. Go too far. And I wind up getting 26.689 amps. And then lastly, I need to figure out the DC voltage required to make that happen, which is literally just going to be using electrical Ohm's law. We have current, we have resistance. We are going to treat our coil essentially as if it were a short circuit because it's an inductance in a DC circuit, looks like a short. So our current, or excuse me, our voltage is just going to be I times R. So that is 26.689 amps times, I believe it was 5 ohms here. Yeah. And we wind up with a voltage of 133.443 volts in order to sustain that 1 Tesla of flux density. Now, technically here, I made a little bit of an assumption that I don't necessarily have an issue with. We were told in the problem statement that we're trying to sustain a magnetic flux density of 1 Tesla in the air gap. I made an assumption that there was 1 Tesla of magnetic flux density in the core as well, but realistically, those two numbers might be slightly different because we allow those magnetic flux lines to spread in the air gap. So this is really just an approximation, but it's going to be pretty close to the answer.
Because of the original form.
Right. So
Would you give us a problem with like 2 separate?
if I were to give you a problem like this specifically on an exam or something, I would probably wind up defining the magnetic flux density in the core and as opposed to the air gap so that there would be no ambiguity.
Are we still doing that take-home portion?
Yes. Yep, absolutely. So for the most part, just looking at our process here, everything except for the last step is the exact same stuff that we had been doing. And then we just circled back around to looking at it in terms of an electrical circuit at the end because we were interested specifically in the voltage or the EMF that is pushing current around and all of that kind of jazz. So now let's take a moment to figure out our stored energy. Just to look at things here really quickly. We're going to be making that same assumption that the magnetic flux density B in the core is the same as the gap, just because it's a reasonable assumption. It's not going to be absolutely correct. We do need to know the volume of our core and the volume of our air gap, right? So those volumes are going to be pretty straightforward to figure out. So how might we figure out the volume of the core, given that we already know the core's length is 60 centimeters? So it's just going to be the length of the core times the cross-sectional area of the core. So it's literally going to be this guy right here multiplied by those two guys right there, because these guys represent the area of the core, right? So volume is going to be 60 centimeters times 5 centimeters squared, and this is going to come out to be 1,500 cubic centimeters. Very similarly, I'm going to write VG, not VAG, because, yeah. The volume of our air gap is going to be the length of the air gap times the area of the air gap. So this is going to be 0.5 centimeter multiplied by 5.5 centimeters quantity squared. And that comes out to be 30.25 centimeters cubed. And from this, I want us to calculate our stored energy. And I'm going to break this down into two distinct parts, right? So we've got the term due to the energy stored in our core. And then we've got the term due to the energy stored in our air gap. So if I put in my numbers here, I'm going to call this 1.0. So a Tesla is a Weber per meter squared, where a Weber is a volt second. So I'm going to write this as 1.0 volt seconds per meter squared, and I'm going to square that whole thing. Down here, I have twice mu c, so that's twice 5,000 4 pi times 10 to the minus 9. So we're going to, actually, I'm going to write it as 10 to the minus 7, excuse me, because I'm going to put it in henries per meter so that the meters cancel each other out. A henry is a volt second per ampere. So I'm going to have volt seconds per ampere meter down here. So are we okay with where those units came from? Not trying to be obtuse or anything. I just want to make sure that you get it. So a henry, let me write it over here. Henry is a volt second per amp.
I think it's just a unit person will set for them.
Yeah. And I'm using 10 to the minus 7 as opposed to 10 to the minus 9 like we used up here, because I want it in henries per meter to cancel out the meters of the Tesla relationship. Doing something similar over here on the right-hand side, we're going to wind up having, oh, actually, sorry, I forgot the volume. So then we're going to have 1,500 centimeters cubed multiplied by 1 meter over 100 centimeters. It won't come out as nicely as that because we have to cube everything. Yep. So this part right here, I'm just going to put an arrow over here. I'm running out of space anyway, is actually going to wind up just being 0.119 joules. So just for the sake of argument, I want to explain how and why this comes out to be joules really quickly, right? So let's see. So I've got a volt second here in the numerator is going to cancel this volt second here in the denominator. I have, sorry, actually that's not entirely true because I'm squaring that. I'm going to be left with a volt second in the numerator. I've got meters to the fourth power in the numerator right now. And then I'm dividing by, I have a factor of 1 over meters in the denominator as well. So effectively for right now, I've got a volt second, a meter to the fifth power. I also have 1 over an amp. So that's going to put an amp up here. Now over on this side of things, that's incorrect. Sorry. That's per meters to the fourth power. And then I have a meters up here as well. Sorry. So the per meters to the fourth power comes from me squaring that Tesla term. And then dividing by volt seconds per amp meters is the same thing as multiplying by amp meters per volt seconds. Okay, so and then I've got centimeters cubed here, cancels the centimeters cubed here, and I'm going to wind up having a meters cubed in the numerator as well. So meters times meters cubed is meters to the fourth. So after all of this crap, we're left with volts times amps times seconds. Well, what's volts times amps? It's a watt, right? And a watt times a second is a joule. Yeah. So Yep, or a joule. Yeah, joule is a watt second, or watt is a joule per second, however you want to remember. Anyway, so that is my term, or that's the amount of energy that I have stored in my core, 119 millijoules. Now let's look at the energy stored in my air gap, right? So by a similar thing here, we're going to have 1.0 volt second per meter squared quantity squared 2 times 4 pi times 10 to the minus 7 volt second per amp meter, multiplying this by my area of 30.25 centimeters cubed, and then my conversion factor of 1 meter over 100 centimeters. What did I forget?
They just there, you know. Well, I wrote U naught, and it was like, oh, we forgot U naught.
It's right there.
Yeah, yeah, right there. I thought there was something else.
Yep. And so this portion winds up coming out to be 12.036 joules. So in total, we wind up having 12.155 joules of energy stored, where 99.018, I want this to look more like a parenthesis and not the number 1, 99.018% is stored in the air gap. So realistically, for a system like this, where we've got a particularly small air gap, we probably could have wound up actually just ignoring the reluctance of the core as well, computed only everything based on what was going on in the air gap, and we would have probably been within 1 or 2% of the final answer to begin with. So just as a heads up, as we saw previously, the reluctance of the air gap is typically much larger than the reluctance of the core itself, especially when the air gap length is particularly small. Since that is the dominant term in the reluctance, it will also be the dominant term in the energy storage of the system. Okay, so talked about field energy for a good bit now. I feel relatively comfortable. Now let's talk about the mechanical energy and force. So I'm going to redraw our little relay picture again. I'm going to just throw this together really quickly. I'm not going to label too much because that's not really the important part. So here's our draw my core here in the middle. And we had our movable part of our relay attached to some spring, right? And I defined, I believe, the X direction as, so I'm going to define it like this. So this is the positive X direction. So when we were looking at our stored field energy, we effectively held that movable part stationary, so that we were working at some specific air gap. Now let's talk about what happens essentially if we let that air gap change dimension. So if we let that part move, okay? So if the movable part moves slowly, then the current should remain essentially constant during the motion. Let me write that down. So if the movable part of the relay. Moves slowly. The current in the coil should be effectively constant. So if we were to look at our flux linkage versus current diagram, it would look something like this, okay? So here's flux linkage on the y-axis yet again. Here's current on the x-axis. And I'm just going to put a dashed line here representing some constant value of current, right? So I'm just going to put I constant down here. So for our original air gap length, our curve might look something like this, where this guy corresponds to an air gap length of x is equal to x1, and at a, and actually let me put some dashes over here too. So where that intersected, we have some flux linkage 1. And after we have allowed it to move, when holding the current constant, we should see that our new curve for a smaller gap length is going to be maybe up here. So this is x is equal to x2, and where it intersects that line, we have some flux linkage gamma 2. Okay. So essentially, what we have had happen is that the operating point of our system is moving from, let's call this point right here, point A, up to this point right here, point B, and I'm going to call this point down here, point O for the origin, okay? So we can throw some math at this, and we're going to. Essentially, what we'll have is during the motion, our change in electrical energy is going to be the integral of EI with respect to time. And this could be expressed as the integral from flux linkage 1 to flux linkage 2 of I d flux linkage. And this is essentially this area right here. Okay. So I called these 2 points A and B. For brevity's sake, I'm going to call this one C, and I'm going to call this one D. So we could call this literally just area A, B, C, D, that rectangle that I shaded in red, okay? Well, the field energy in the system has also changed, okay? Where our differential field energy, dWF, is going to be the area of OBC minus the area OAD. So let me just try to, I'm going to wind up erasing this in a second, but I just want to demonstrate what these areas are really quickly, okay? So OBC is that total area, and OAD is that area in pink. So our field energy, our change in field energy is just the difference of those two areas, right? Because everything above that line or above our curve was our field energy. So we can relate these two things together from our expression earlier, where our mechanical energy is going to be just our electrical energy minus our field energy. And so if we look at this, that's going to be the area ABCD minus the area of OBC minus the area of OAD. And this comes out to wind up being the area OAB. Should accidentally erased my second curve. Let me put it back here. So essentially, our mechanical energy, I guess do it in green, is this bit right here. And that just simply represents an increase in the co-energy of the system, right? Where the co-energy is measured the area below the curve, right? So we had some amount of co-energy that was down here before we allowed our gap to get smaller. Allowing the gap to get smaller increases that overall co-energy, and that change in energy is just the distance between those two curves. Okay. So we could say then that our change in mechanical energy is simply the change in the co-energy, WF prime. And if Fm is the mechanical force causing the displacement, let's call it x2 minus x1 is equal to some differential change in x, then our differential mechanical energy is just going to be Fm dx. So before I move on from here, I want to ask you guys a really quick and simple question. You guys have had like your version of statics and physics and all of that kind of good stuff, right? How many of you guys remember Hooke's law? Not even necessarily the equation, but what do you remember about what Hooke's law applies to? So you remember the name, okay?
The name sounds familiar. The name feels familiar. I have no idea.
Springs. F is equal to kx, right? Yeah. So this is effectively just us describing Hooke's law for this particular system, where we're not necessarily worried about the spring constant per se. We're just putting things in terms of, hey, if I put electrical energy in, what's my change in displacement? So I'm treating that change in electrical energy almost as if it's manipulating the spring constant of the system. That's all that's going on here, right? So from this, then, so we could say that this is just the change in our co-energy. We've already talked about that. And thus, our force here for a slowly moving thing is just the partial derivative of our co-energy as a function of I and position over our change in position where we hold I constant. Now let's look at the flip side of things. So this is one extreme to where we're holding the current constant and we're causing the co-energy to change very, very slowly, or we're causing the position of our spring to change slowly. Brock. WE is electrical energy, WF is field energy, WM is mechanical energy. The D in front of it just means we're looking at how it changes over a very small interval of time.
And then what is O? So it's like,
Yes. But so what you guys probably learned as delta, if you have like a rigorous calculus background, is D. Like that's what a derivative means, is the change in something. And so we use that D to represent an infinitesimal change or a differential element in a particular direction. So dx just means a very small slice of the distance between 2 points along the x direction. All right, so we're going to look at the other side of things now, where what happens if we allow our plate to move very quickly. Okay. O, like this O right here, that's literally just the origin point of our system.
oh. So it's really just X0.
Yeah. No zero. So yeah, no movement in our extra
Nope.
zero current, zero flux linkage. All right. So for a fast movement, the flux linkage will remain constant during the motion. So essentially, if I were to draw a very similar graph to the one I drew a few moments ago, where here's my flux linkage, here's my current axis, here's some arbitrarily constant flux linkage, lambda constant. So my two curves will be essentially the same type of thing, something like this. Actually, that doesn't actually hit that line, so let me make it a little bit more exaggerated. And then something like this. So this is for a gap length of x1. This is for a gap length of x2. We now find that we have two different currents where this guy intersects, right? So where it intersects curve 1, we're going to call this I1. Where it intersects curve 2, we're going to call this I2. So if I call this operating point A and this operating point P, the operating point on our system has just shifted from point A to point P on our particular lambda I curve. Okay. So let's make some observations about this particular situation. Okay. So I think that the electrical input energy didn't change. And the reason why I'm saying that is because I times the change in flux linkage has to be 0 if the flux linkage is constant, right? So we don't have any electrical input energy change. So that means that dWf plus dWm for this system has to be equal to 0. So earlier we said dWf plus dWm was equal to dWe. That's this guy right here, essentially rearranged, where I'm just moving the electrical force, excuse me, the mechanical, the field energy over to the same side. We can actually just look at this thing and say, hey, if dWe is 0, dWm is going to be equal to negative dWf, which is literally what I'm about to write down anyway. So dWm will be equal to negative dWf. So essentially, the mechanical energy is the decrease in the field energy. Not going through all of the areas and all of that kind of good stuff. That mechanical energy is essentially going to wind up being this area yet again, which is exactly what I mentioned. It's the decrease in the field energy. And so relating things back to what we did up here, we could say that our mechanical force in this particular case, I'm going to put it under or inside absolute value sign. So I'm just looking at the magnitude of my force. Okay. So we'll have the change in field energy as a function of, sorry, getting a little bit ahead of myself. Now, flux linkage and position with respect to position when our flux linkage is held constant is our force. And then finally here, for a linear system, where we can say that B is simply equal to mu H and or our air gap is large enough such that our flux linkage current curve is linear, then our force Fm is going to be the derivative of our field energy as a function of gap length with respect to gap length. So our force generated is only caused by the change in our gap length. And so I'm going to take the derivative of this thing. So I'm just going to plug in our field energy equation that we came up with at the end of last class. So D over D with respect to LG. I've got a BC squared over 2 mu C. I'm going to choose to represent this volume as the area of the core times the length of the core. Then I've got my air gap term BG over twice mu naught, AG, LG, like so. I'm going to ask you guys a question. It's okay if you don't know the answer to it, but what's the derivative of a constant? 0. So the reason why I asked that specifically is because literally none of that term right there for what's going on in the core has anything to do with the gap length. So the derivative of that whole first term is 0. And so all we're left with is BG squared over twice mu naught times AG. So essentially, sorry, that looks too much like an O. Only energy stored in the air gap will contribute to the mechanical force. So if we used our previous example and we wanted to calculate, so just as a quick aside here, the force acting on the movable plate from the previous example. Our force would be Fm is equal to Bg squared over twice mu naught times Ag, just throwing in numbers here. So this was 1 Tesla, so 1 volt second per meter squared over 2 times, excuse me, 4 pi times 10 to the minus 7 volt seconds per amp meter. Our area was 30.25 centimeters squared times 1 meter over 100 centimeters quantity squared. And this comes out to be 1,203.609 newtons per air gap. Nope, because we're doing area, not volume. So all in all, if we put 133 volts across our relay, we would be putting damn near 1,200 newtons of force trying to pull that plate in to close those bad boys if our initial air gap was half a centimeter, or excuse me, half a millimeter. That is indeed a lot of newtons. That's a big relay though, 10 centimeters cubed. All right, so let's look at something else real quick here. Where did there's page 5? 6.
Bless you. Because these are all over the gap, because you're finding that the. That's the volume,
So let's go back up here and let's look at it because I think I understand what John is asking about. Not John, Jake. So we had 30.25 centimeters cubed. Right, actually, hold on. Let me, you're right. I may have made a mistake here. Let me get my calculator. So I should just have 5.5 centimeters times 5.5 centimeters. Let me see what that shakes out to be. Trying to remember how to get my calculator out of whatever the hell function it was. So 5.5 centimeters times 5.5 is 121 over 4 or 30.25. Maybe that volume is wrong, man. Yeah. That come out to be, sorry, 5.5 squared times 0.5, 121 over 8. So this should be half as large, sorry. 15.125 should have gone here. Thank you for that catch, which is going to change this guy to 15.125. So this term was probably going to be half as large. So let's just call that 6.0 something joules. Still, the overwhelming majority of the energy was stored in the air gap. So got that little bit of math incorrect.
What they're trying to do?
15.12, it's half as large because we're multiplying by half a centimeter.
But the answer is still 12?
No, that's also going to come out by a factor of a half. Yeah. Let me fix that. Let me just throw that bit in my calculator and I'll give you an exact answer really quickly. So 1 over 2 times 5,000 times 4 pi times 10 to the minus 7 times, sorry, 1,500 over 100 cubed. Shit, that was the wrong thing. I did the other one. Damn it. Well, that was right for what it's worth. 1 over, sorry, 2 times 4 pi times 10 to the minus 7. And then 15.125 over 100 cubed comes out to be, yep, 6.018 joules when I add those guys together.
6.137.
Yep, 6.137 joules. And for what it's worth, 6.018 over 6.137 comes out to be 98.06%. Yeah. So still overwhelmingly, the energy stored in that system is due to the air gap. Okay. All right, my apologies for that mistake. So let's look at something here.
We didn't forget the answer for the static support. Sorry.
Yep. Okay. So I want us to calculate the average force acting on the movable plate if a 120 volts RMS at 60 hertz voltage were applied by our voltage source. Okay. So I want to, we're using essentially this previous example. Let me take a look at it again, okay? All of these things are still going to be roughly the same, right? So does the coil reluctance care whether or not I have an AC voltage or a DC voltage, or AC current or DC current? Not at all, right? So that equivalent reluctance that we calculated is still legit. Now, when we got down here and we calculated our DC voltage and stuff like that, I said that we could just use Ohm's law, I times the resistance here, and we didn't have to worry about anything else because our coil was essentially behaving as if it were a short circuit because we have a DC system, and so that inductor is going to look like a short. We now have an AC system, so that inductor is no longer going to look like a short. It's going to contribute some impedance to the system, okay? So we're going to need to figure out what that impedance is. So I believe this was covered in one of the videos that you guys watched while I was sick, but we talked about how to determine the inductance of a coil based on its equivalent reactance, right? And that relationship was simply n squared over equivalent reluctance. So that would be 250 turns squared divided by 2.669 times 10 to the 6th amp turns per Weber. So I just want to remind you all that a turn is a dimensionless quantity, so I can literally just throw those away with impunity. So what I'm going to wind up getting here, and let's throw this into our calculator so I can make sure I'm not screwing something up. 250 squared divided by 2.669 times 10 to the 6th, right? It's the only thing that we've got here. I wound up getting 0.0234, and I'll keep on going here for a second, 170. Now let's talk about these units really quickly, okay? So I have nothing in my denominator, nothing in my numerator has survived. And in my denominator, I have amps per Weber, which is going to look like Webers per amp. So a Weber is a volt second per amp, which is, what's that, Brock? What's a volt second per amp, since you asked me about it a couple of minutes ago?
Did you?
Nope.
No?
A Henry. Yeah.
Is it?
Yeah. Yeah, that's exactly.
No, that's just some random child that you
Yeah,
found.
about that following.
I've never seen his kid, right?
So 23.417 millihenries is what I wound up getting here. Okay. So our overall impedance then, Z, is our 5 ohms of resistance plus J. So what should our angular frequency be here if we know that our excitation frequency, our linear frequency, is 60 hertz? Sixty hertz is linear frequency. I want angular frequency. What's the relationship between those two things?
Or, wait, I don't know.
If I give you, let me scroll down here. If I give you F and I want omega, what do I need to do? You guys are just pissing in the wind.
Yeah, pretty much.
F is linear frequency. So, sweet mother of God.
Hang on.
Nope. We'll sort it out. I will burn this into your brain. Let's say that I have a sinusoid. Oh my God.
We already cooked. Guys, I think we're cooked.
Here is time, right?
Sinusoidal wave. Oh, so we gotta use funny, cosines and stuff?
So if I had drawn this well, I'm attempting to, okay, just for what it's worth. The distance between these peak values is capital T, the period, okay? So this represents, spelled that shittily, period, time it takes for one cycle to complete. So if I take the reciprocal of t, so this is the inverse, instead of the time it takes for one cycle to complete, this would be the number of cycles in 1 second, okay? So this is what's known as our linear frequency, and it is inversely related to this. So this is linear frequency. And essentially, this is the number of cycles per second. Okay, hertz, exactly right. Angular frequency is essentially how long or the number of cycles it takes for us to get to 2 pi radians. So we literally, yep. Omega is just 2 pi f. This is our angular frequency. And so this is the inverse of how long it takes us to get through 2 pi radians of degree movement. Anyway, so coming all the way back up here, I ask you guys again, if my linear frequency is 60 hertz, 120 pi radians per second. Absolutely right. What was that, Brock? Radians per second. Always, always, always. Multiplying this by 23.417 times 10 to the minus 3 volt seconds per amps winds us, so the seconds and the per seconds cancel each other out. Radians is the dimensionless quantity. Volts per amps is just the same thing as an ohm. So we're just going to wind up with 5 ohms plus J some number of ohms. And this comes out to be, if I did this correctly, which I believe I did, 5 plus J 8.828 ohms. All right, so if I know the voltage and I know the impedance, how do I find current? So what do I do? It's Ohm's law. What do I do?
I was D times D over R.
V over Z, because
Yeah.
Z is playing the role of, yeah, okay. So the magnitude of our current, which I'm just going to call that IRMS, is going to be the magnitude of our voltage divided by the magnitude of our impedance. So I could write this impedance for what it's worth as 10.146 angle 60.475 degrees ohms. So this is going to be 120 volts RMS divided by 10.146 ohms, and I wind up getting 11.827 amps RMS. So that is the amount of current that is flowing, and I need to use that information in order to essentially figure out the average value of the magnetic flux density. So let me circle back around here so that we can remember what the hell it is we're doing, because this is an involved process, okay? So ultimately what we're trying to do is apply this equation that I've just underlined, okay? 2 mu naught and Ag are literally constants for this system. So essentially, in order for me to calculate that force, I need to be able to figure out what B is, okay? So how are we going to figure out what B is given what we have right here? So let's look at Ohm's law for magnetic circuits, and let's see if we can sort some things out based on what we know, right? So I think we have learned previously in this class that N times I, and I'm just going to call this IRMS for right now, is going to be equal to flux, and I'm just going to call this the RMS value of the flux, times our equivalent reluctance. Has anybody got any beef with that? That is literally Ohm's law for magnetic circuits, where MMF is equal to flux times reluctance. This is like second or third day of class kind of thing. We are all okay with that. How can I make this flux term relate to the B that I'm looking for? What's that relationship? B times A. Absolutely right. So I'm going to do B RMS times A for my, let's see if we're doing magnetic flux density in the core or in the air gap, doesn't matter, we're using the same thing, but I want to make sure I'm using the right area. Let's do the core. BRMS times AC times REQ. And again, this is going to be, if I had used the area of the air gap here instead of the area of the core, the number would be slightly different, but we're going to get something very, very similar regardless of which one we use because the areas are so similar. Okay. So if I rearrange this guy, I should be able to say that the average value of the flux density in the core is just Ni over A reluctance, right? So that's going to look like 250 turns, 11.827 amps, 25 centimeters squared, and then, excuse me, 2.669 times 10 to the 6th amp turns, excuse me, per meter. Amp turns per Weber, goodness. And then so if we look at our units here just really quickly, amps cancel amps here, that's fine. I've got per Weber, so that's going to be okay because, or I've got 1 over per Weber. I'm going to have Webers in the numerator, so that's fine. So I have Webers per centimeter squared, and a Tesla is a Weber per meter squared. So I'm just going to convert between centimeters and meters to make things work out right here. Okay. So let's see, 100 centimeters up here, meters goes down here, square this whole thing, and I wind up getting 0.443 Tesla. So just as a quick aside type thing here, I want you guys to notice earlier on, in this previous example problem, we found out that a voltage of 133.443 volts DC generated, that was what was required to generate a magnetic flux density of 1 Tesla, okay? Now we're dealing with 120 volts RMS, but 120 volts RMS is literally the DC representation of some AC signal, okay? But because we have an AC signal, we're generating about half of the amount of flux that we had when we just put in a DC term, okay? So we are going to generate significantly less magnetic flux density with AC signals than we will with DC signals. Just trying to make you guys aware of that. All right. So from that, the RMS force generated by this voltage is going to be our RMS magnetic flux density over twice mu naught times AG. So that's going to look like 0.443 Tesla quantity squared, 2 times 4 pi times 10 to the minus 7 henries per meter. And then our area was 30.25 centimeters squared. And then 1 meter over 100 centimeters quantity squared. This winds up coming out to be 533.390 newtons per air gap, essentially. So a little bit less DC voltage. The reason why I'm making the comparison between the DC and the AC voltages is because their magnitudes are so similar, right? 120 isn't that far away from 133 volts, and we are getting roughly half the magnetic field and therefore half the force because we're using the AC voltage as opposed to a DC voltage. All right, I have talked at you guys for almost an hour and a half straight. So lecture is now officially over. There's more stuff that I have to cover, but this is a good stopping point. If you have any questions about homeworks and stuff like that, I'd be happy to answer them now.
Right.